let's see what are the challenges or what are the issues with this RCNN, and that will lead us to fast RCNN, which is the next in this series. Now, there are actually not one, several issues with RCNN. First of all, it's very slow during runtime. Okay? And the reason for that is you're actually getting multiple proposals. Okay? So, and these proposals can be overlapping. And there could be a lot of overlap, because you can assume that this is a very small image, and if you're getting 2000 proposals, there is going to be a lot of overlap. And what we discussed earlier in RCNN, for each proposal, you're actually extracting a feature, right? Because each region proposal, you reshape it, and then you pass through the CNN to extract the feature. So if you think about this, if you have 2000 proposals in an image, you're actually doing that feed forward step 2000 times, which is actually not required. A lot of that is redundant. Okay, so that's first issue, and we will see how that can be solved in fast RCNN. And the idea is, instead of having multiple passes, we just do a single pass for each image and extract features. And again, that's a very, very interesting concept. Okay, before talking about that, we have I think one or two more issues. Second issue is we have to train separate classifiers or separate SVMs for each class category, which is not efficient. I mean, with 20, it was 20 classifiers. With 1000 objects, it will be 1000 different classifiers, right? So it's not scalable. Now, the idea was how we can fix that, and we can actually do end-to-end learning where we don't need SVMs. Okay, so that will be the solution. The third issue was the complex training pipeline, because first you have to figure out what are the region proposals. Then for each proposal, you reshape, you extract features, save features, then again load features, train your SVM classifier. Very, very complex pipeline, right? So we'll try to simplify that a little bit. And what we'll need is just a single forward pass for each image, which will do all of this together. Okay, so the solution is it's called fast RCNN, and we have three different items to discuss here. We will do a single forward pass instead of multiple passes. We won't be having separate classifiers for different classes, and it will be end-to-end learning. Okay, so this is again similar kind of architecture. Now the interesting part is, instead of applying the region proposals on the input image, we apply these region proposals on the activation maps. So we take the input image, pass it to CNN, extract the features. Let's say this is your activation feature activation map. So these are already your features. Now on top of, since your CNN can preserve the spatial structure, right? So then you can actually apply these region of interest, or you can say maybe some kind of region proposals on these activation maps. And instead of reshaping your input sample or input image, you reshape these features. And what we need for that is called ROI pooling. This is a region of interest pooling. You will heard this term a lot. Okay. And this ROI pooling is required because the same way we need to reshape your region proposals to same shape, we need to do the same thing here as well, because your different feature sets should be having same dimensionality, right? So for that, we need ROI pooling. We'll discuss about how exactly this is done. So once that is done, then each of these regions will have same number of features, which again you can flatten and use them as features and directly do classification. So this is your softmax classifier head, and this is again a linear layer, which is giving you bounding box regressions. Okay. Now in this case, we don't need separate SVMs. So this is end to end, and we don't have to pass the patches independently through your CNN. It's just done once. These two steps are mainly optimized. Okay, so it will look something like this. Given your input image, let's say if this is your region proposal, you will first extract features from your image and then apply this proposal on that feature map. So you'll have to do some kind of scaling because the resolution of your feature map will also reduce, right, corresponding to your input image. So you'll have to perform same kind of scaling to your bounding box as well. And then you will use features only from that location to bring them down to a certain shape. And that step is called ROI pooling. And rest, I think, is trivial. You have those features, you make softmax predictions, you can make like a bounding box regression. Okay, so this is same, but it's just like you don't need SVM for that. You're using neural network for it. Now, I think this part was easy, how this can be done end to end, because instead of training SVM, we are just training neural network. This part is something new, so let's spend some more time on this. Okay, how to perform region of interest pooling. Now, given an image, you extract feature map. If your input image is 3 cross 800 cross 600, 3 is like for 3 different channels of a color image. So after extracting features, it might reduce to C times H times W, right? This is height, this is width, and again, this is number of channels you have. And again, it will vary from like network to network, but still you have this kind of spatial structure. And in a way, we can say that, okay, in this height and width, each location, we can say that, okay, which region this pixel belongs to, okay, or this activation belongs to in the input image, and that is called receptive field. So not exactly receptive field, but there is some correspondence. Receptive field is actually what different pixel values were actually used to obtain this activation. And usually like in CNNs, if you go deeper, your receptive field is like the whole image. Okay, so that's slightly different, but the idea is to find one-to-one correspondence. So in this case, you know that how much of your image has downsampled because you know these numbers and you know value of H and W. So we'll perform same kind of transformation to your proposal box as well. We'll try to fit it here on the feature map. And then you will try to extract these activations into like a fixed grid, which will have, let's say, a shape H cross W, because we want to bring all the proposals to same resolution. Okay? Something like this. Of course, number of channels is not going to change, but what's changing is the shape of this. If it's H cross W, it's coming down to small h, small w. So ideally at the end, it doesn't matter like what was the shape of your proposal in the input image. Every proposal will have feature vector, or you can say activation map of this shape, C cross small h cross small h. Okay, so let's try to understand how this step can be done. And of course, you can backprop through this because this is kind of max pooling operation we are doing here. And you know, max pool is differentiated. All right, so this is your input image, and let's say this is your proposal. And of course, you are creating those proposals. You will have the dimensions, the height and width, and the exact location. And you will try to map that exactly on the activation map. Let's say your input image is 600 cross 600, and your proposal is like 200 cross. This is something 145. So don't pay too much close attention to its exact number, but just try to understand the concept. And let's say the image resolution is actually going from 600 cross 600 to 16 cross 16. This is your activation feature map size. So if you try to map this bounding box over this, it will lie something like this. Now, the tricky part is, since the resolution of your image has reduced a lot, which means each location in this grid actually corresponds to multiple pixels, right? And because of that, this bounding box will not perfectly align with this grid. Okay, so now the question is, if you have to do max pooling on that, how do you make adjustments? And there are different ways. I mean, you can try to increase the size and try to fill it properly. And usually I think a ceiling operation is used. So if it's here, you just find like the closest corner. Okay, so that will be the adjustment you will have to make. So the red one is the actual proposal in your input image, but after adjustment, it becomes like this orange region over here. Now, if you think about this, some of these pixel values over here were used to extract these activations. but in fact, we are not using that after ROI pooling operation. And that's kind of one of the limitation. We are actually losing information. And if you pay attention to like this region here, this is like additional information which we didn't want, because these pixels actually lie outside this bounding box. So kind of if you look at the green region, that's something which we didn't want, but we have to sacrifice with that. And again, blue is something which we wanted, but we have to get rid of that. And so that's like one way how you lose information. There is one more way how you lose information. For example, if you have activation, something like this, activation map. Okay, so this is in this case 4x6 area, and we want to map this to 3x3. Okay, so what you do is you try to divide this into like 3x3 grid, and you just perform max pooling. Okay, so these 2 pixels, you pick the max one, and again these 2 pixels, you pick the max one. And you can pick like average pooling as well. It's perfectly fine. You can have different variations, but you will have to ignore the last row because that's kind of not fitting into picture, right? How will you use that information? Because it's not actually completely dividing. So again, this is loss of information. So multiple ways like how we are losing information, and later we will see like how we can address this. But at least in fast RCNN, this is how it was done. Okay, so this is like the lost data, which is fine. Now let's try to compare with, some stats between fast RCNN and RCNN. In terms of training time, it took like roughly 84 hours. Okay, and again, this is VOC dataset. Fast RCNN reduced that to just 9 to 10 hours. Okay, so a lot of reduction in training time. So again, testing time, it was 47 seconds. And you can see like it's fraction of a second. And performance, it's like almost the same, 66 and 66.9, not a huge improvement. But if you look at these numbers, these are amazing. And you can guess like why this happened, because we saved like a lot of computation costs there, right?